Hey everyone, it's Justin again. In this unit, we'll be learning about graphs of rational functions. But first, we should review an important topic that will come up frequently in the next few lessons: domain and range. By the end of this lesson, you should be able to identify the domain and range of functions from graphs and equations. First, we'll review the meaning of domain and range. After that, we'll practice identifying domain and range from graphs of functions and identifying domain and range from equations of functions. Then we'll work through a couple of examples. You may remember that the domain of a function is the set of all possible numbers that can be inputs, or x values, and the range of a function is the set of all possible numbers that can be outputs, or y values. For the purposes of this lesson, you won't need to write answers in any specific mathematical format. We could describe them in words like this. So let's review how to come up with these answers. We'll think of the function f of x equals x squared as a machine. Machine? Yes, a machine. You feed something into this machine and it gets turned into something else. The things that you put into the machine can be thought of as the domain, and the things that come out are the range. So let's try throwing in a 7. Our machine multiplies the input number by itself to get the output, in this case 49. So 7 is within the domain of x squared, and 49 is within the range. We can put any number into this machine because you can multiply any number by itself without running into problems. Therefore, the domain of this function is all real numbers. But although the domain includes all numbers, the range of this function does not include any negative numbers. No matter what real number you square, you can never end up with a negative answer. Now, if x squared can only be 0 or higher, how is that fact represented on the graph of this function? You can get infinitely large positive numbers, so the graph will keep going up and up forever and ever. But the graph never goes below the x-axis, because you can never get a negative number by squaring. That corresponds to the range, the possible outputs being all numbers greater than or equal to 0. How about the domain, the possible inputs? If your input is 1, you get 1. If your input is 2, you get 4. Your input is 3, you get 9. It's off the graph right now, but that doesn't mean you can't square 3. All it means is that we're only looking at part of the function here. A 4 would give you 16, and so on and so forth. You can square any number you want, and you'll always get a valid answer. So although the graph looks like it's curving further and further up, it also keeps going further and further to the left and the right. The domain might look like this at first, only existing in this middle section of the graph. But that's just because the graph can only show part of the function at a time. The actual domain is all real numbers. If you had a big enough graph, you could keep graphing it to the left and right as far as you wanted. Let's try and find the domain and range of another function, the log base 10 of x. Think about the machine we used earlier. The log base 10 is a machine that takes in a number and gives you the power to which you would need to raise 10 to get that number. For example, the log base 10 of 1,000 is 3, because 10 to the third power is 1,000. Remember, the domain is all numbers we can put into the machine. Do you recall what numbers we cannot put into a log function? If right now you're thinking, what were those log rules again? Don't worry. For at least this lesson, the main thing you need to remember is that you cannot take the log of 0 or the log of any negative number. So if we can't do logs of negatives or 0, then those are the numbers that we cannot put into this machine, which means that those are the numbers that are not in the domain. Sometimes the domain is easier to see on the graph. In this case, there's a vertical asymptote at x equals 0, which is also the y-axis. Remember that an asymptote means the graph gets infinitely close to that value, but never actually touches it. The function exists on the positive side of the graph, but it can never cross 0 into the negative side of the graph. So the domain of this function is all real numbers greater than 0. As for the range, although it may not look like it from this graph, the right side does go infinitely high. You can pick any positive number, and there will always be some input you can choose that will give you that output. To see why this is true, why don't you pick any number between 1 and a trillion, and I'll show you why no matter how big a number, it's still included in the range. Was your number 434,920,011? No need to answer that. I know I got it right. Well, the number you can put into this function that would give you that output is 10 raised to the 434,920,011. Any possible number can be an output of the log base 10 because you can raise 10 to any power, and that power would be the output. Therefore, the range of this function is all real numbers. The moral of this story is, just because a graph looks like it's flattening doesn't mean there's an asymptote. The log function does keep going up infinitely far, just very slowly. So be careful when you're finding domain and range from a graph. Sometimes you may prefer to use a graph, but always make sure to double check your work with the equation. Before we move on to examples, let's create a list of ways to restrict the domain of functions, meaning ways that the domain of a function might not be all real numbers, like our example with 0 or negative numbers inside of logs. There aren't too many reasons you can't plug certain numbers into functions, so having a short list will be helpful when we work through examples. Think about all the different types of functions that you've seen. Which of these other functions might not work if you try to plug in certain numbers? The square root of x and 1 over x are functions that can cause problems. You don't get a real number if you have a negative inside a square root, and you can't put 0 into a denominator. The cube root of x is actually fine because you can take the cube root of a negative number. So it's only even numbered roots that we have to worry about. So here's our list of things to look out for when we're checking domains: even roots, logarithms, or an x in the denominator. You may not have graphed any functions like 1 over x before. That's for another video. For now, you should just recognize how that restricts the domain. For example, the function 5 over x plus 6 would have a domain of all real numbers except negative 6. Since negative 6 is the value of x, that would make the denominator 0. If anything on this list appears in a function, you should double check to see if there are any numbers you need to kick out of the domain so that they don't cause trouble. The nice part is, if a function does not have any of these complications, you can assume its domain will be all real numbers. There are technically more ways than these to restrict the domain of functions, but these three are probably the only ones that you've seen so far. So these are the only ones that you would be asked about right now. All right, now we can start on some examples. Here's the first one. What's the range of the function shown? Recall that the range is all possible outputs or y values of the function. It looks like the function will go infinitely far upward, so it's just the lower boundary that we need to look at. This function goes no lower than negative 3. So the range is all real numbers greater than or equal to negative 3. That's the answer. Here's an example with an equation rather than a graph. What's the domain of this function? To answer questions about the domain, we should always think about that list. Things inside even roots, logarithms, and denominators can cause problems. Here we have an x in the denominator. If there are any values of x that would cause a 0 to be in this denominator, we need to exclude those values from our domain. So what values, if any, would cause the denominator to be 0? If x were equal to 4, that would cause the factor of x minus 4 to be 0. So that would make the denominator 0. However, if we try to solve for the value of x that makes the factor of x squared plus 4 equals 0, we end up with x squared equals negative 4. Because that has no real solutions, this x squared plus 4 factor does not restrict our domain at all. We only have to worry about when x equals 4. Therefore, the domain of this function is all real numbers except 4. In this lesson, we reviewed how to find domain and range of functions from its equation or graph. Remember that list of domain restrictions. It'll be useful for practicing this skill. Next time, we'll review how to write domain and range in what's called interval notation, which will be very useful throughout this unit. See you then!